Okay, so in this video, we are going to define matrix multiplication. Now, if you remember matrix addition and subtraction, we could only add matrices of the same size, and we would simply add corresponding entries. And you may wonder, well, is it the same thing for matrix multiplication? If we have two matrices of the same size, we could multiply their corresponding entries and define multiplication this way, between two matrices. This would actually make sense, but it would not be very useful matrix multiplication. What we're going to see in this video is a different matrix multiplication, which will be a little more complicated. But as we will progress more and more in this course, we will slowly understand why it is the more useful, more natural definition. Before we go on, let's look at a few simple definitions to save ourselves a bit of writing. So we denote R, we write m times n. This is the set of all m by n matrices with real coefficients. Or if you prefer, entries. So instead of writing, say, if you take a matrix A, instead of writing A is an m by n matrix, we will simply write A belongs to, right? This is the symbol belong to the set Rm by n. So this means that A is an element of this set. This is the set of all m by n matrices with real coefficients, with real entries. And so if A belongs to this set, A must be a m by n matrix with real entries. Let's look at two simple classes of matrices, row matrices and column matrices. And I'll define them by showing you examples. So here's one matrix, let's say 1, negative 9. Here's another, let's say 1, 0, 3. And here's another, 0, 9, 8, 5. These are called row matrices as they consist of a single row, and we call the length of such a matrix the number of entries, the number of coefficients. So this is a row matrix of length 2. Because it is a single row and consists of 2 entries, this is now obviously a row matrix of length 3 because it consists of 3 entries, and this is a row matrix of length 4 because it consists of 4 entries, and so on. So in general, a row matrix of length n is a single row with n entries. And you obviously have the analog column matrices. I could look at the matrix 1, 5, the matrix 1, 3, 2, and the matrix, say, 5, 0, 6, 1. Well, this is a column matrix of length 2. Obviously, this is a column matrix of length 3. And this is a column matrix of length 4. So in general, if you have a column matrix of length n, it is a single column that contains n entries. And now, so we will define matrix multiplication first between a row matrix and a column matrix. So here's our first definition. Let's take a simple example, and then we will generalize. So if I give you, say, a row matrix of length 2, say 1, 3, and a column matrix of length 2, say 9 minus 2, the question is, how can we multiply a row times a column matrix? And the way it's done is we multiply corresponding entries, so the first entry of our row matrix times the first entry of our column matrix plus the second entry of our row matrix times the second entry of our column matrix. So quite simply, we multiply corresponding entries, so first with first, second with second, and we add them up. So in the end we have 9 minus 6, which gives us positive 3. So the result of this multiplication, this row times this column, equals 3. Let's look at another example. What if we have a row matrix of length 3 and a column matrix of length 3? Say 1, negative 2, 5 times 6, 1, 3. Well, once again, we'll do the same thing. We will multiply corresponding entries and add them up. The first entry of our row matrix times the first entry of our column matrix, so 1 times 6, plus the second entry of our row matrix times the second entry of our column matrix, plus the third entry of our row matrix times the third entry of our column matrix. So once again, what we did is we multiplied corresponding entries, first with the first, second with the second, third with the third, and then we add the products up. Well, this is 6 minus 2 plus 15. 6 minus 2 is 4, plus 15 is 19. And so the result of this row matrix of length 3 times this column matrix of length 3 is 19. And you see in both cases you obtain a real number. What if we tried the following? Say we tried 1, negative 3, 4 times 6, 7. The question is, does this make sense? If we base ourselves on our previous two examples, we have to multiply corresponding entries and add them up. So if you did, well, 1 times 6, so far so good, plus negative 3 times 7, plus 4 times, and there's an entry missing here, right? There's nothing here, and for that reason, this product is not defined. You can only multiply a row matrix with a column matrix, so a row times a column, if they both have the same length, because we multiply, and the keyword is corresponding entries, and we add them up. And the only way to do so is if our row and our column have the same number of entries. So in this case, this is simply not defined. And this is our conclusion for a row and a column. You can multiply a row times a column matrix as long as they have the same length, the same number of elements, and you multiply their corresponding entries, and you add them up. If they have different length, then you cannot perform the multiplication, and so the result is simply not defined. So let's write our conclusion when we multiply a row times a column matrix. So we will let A be our row matrix. Now, if you remember, a row matrix is a single row, so it will be a 1 by, say, n matrix, right? It is a 1 by n matrix, so it is a 1 row n columns, so it's a row matrix of length n. And let B be now a column matrix of length, say, m. So m by 1. M rows, but a single column, and so B is a column matrix of length m. Then we can perform A times B. So it is defined if and only if, right? This double-headed arrow means if and only if. Well, if they have the same length. So if n is equal to m. That's the first part. Now, if n equals m, if they have the same length, then how do we perform the multiplication? Well, A consists of one row, n entries. So you can label the entries, say, by A1, A2, up to AN, times the column B. Now, if n and m are equal, B will be a column matrix of length n. So you can write B1, B2, up to Bn. And how do we perform this multiplication? We multiply corresponding entries and we add them up. So A1 times B1 plus A2 times B2 plus A3 B3 plus up to AN times Bn. And notice that the result, and this is important, of a row matrix times a column matrix, as long as they have the same length, is always a real number. And this is how you define the result of a row matrix times a column matrix if they have the same length. If not, then AB is not defined. With this, we can now extend this multiplication to rectangular matrices. As we will see, it is not always defined. One last little observation. If you look at the size of our two matrices, right, this is matrix A, this is matrix B. This is simply a small remark. So A is a 1 by n matrix, and B initially, if you go back, was a m by 1 matrix. And you see the only way for A and B to be defined is if n equals m. And so you see the number of columns of A must equal the number of rows of B. So both of these must be equal. And what's interesting is, if you think of it, the end result, A times B, is a real number. But you can think of a real number as a 1 by 1 matrix. And if you look here, 1 by 1 is a real number. And this will actually work out for more general rectangular matrices. So keep this in mind. You can only multiply A and B if the number of columns of A equals the number of rows of B. If they are equal, the new matrix AB will be of size number of rows of A by the number of columns of B. So now with this, we can look at a general multiplication between A and B, where A and B are arbitrary rectangular matrices. So we will take two arbitrary rectangular matrices. So let A be a m by n matrix, and B be a, say, P by Q matrix. So we have two rectangular matrices. So first part, A and B is only defined if n equals P. So we can multiply A and B. So A times B is defined. If and only if the number of columns of A equals the number of rows of B. So if n does not equal P, A times B does not exist. But if n equals P, then A times B is defined. Now part B, the question is, well, if n equals p, what is the size of AB first, and then how do we compute its entries? So if n equals p, then the new matrix AB, and I leave myself a bit of space here to show you the trick. A is an M by N matrix. B is a P by Q matrix. So if n equals P, number of columns of A equals the number of rows of B, the multiplication between A and B is defined, and the result will be a matrix, and it will be a M by Q matrix. So M rows by Q columns. So that's the first part. So if n equals P, you can multiply A times B, and the result will be a M by Q matrix, where the question is now, how do we compute the entries of A times B? Well, let's see. So we take our matrix AB and consider an entry in the ith row, where I is any real number, well, any integer between 1 and M, and J is any integer between 1 and Q. Right? If you remember, when you put round brackets around a matrix, here the matrix is AB, that means that we're looking for entries of the matrix, entries where? In row I, column J. The great thing is we have two matrices, two indices. I is the row index, J is the column index, and we've already seen how to multiply a row times a column matrix. So we will take simply the ith row of matrix A, so the first index goes with the first matrix, times the jth column of B. And that's it. So if you want the entry in the ith row, jth column of the new matrix AB, you take the ith row of matrix A, so first index with the first matrix, times the jth column of the second matrix, B, second index, second matrix, and you will find the single entry in AB in row I, column J. Now this is what we use for computations. We will very shortly look at properties of matrix algebra, so matrix addition, subtraction, and multiplication. And to prove those, we need a slightly better way of writing this out. Well, let's write the ith row of A. So it is the entry first A, we're in the ith row. The first index is always I, so AI1. Then it is AI2 up to AI. And if you think of it, A is an M by N matrix, so there are N columns. So it stops with AIN times the jth column of B. Well, we are now in the jth column, so we fix the second index being J. This would be B1J. Second row, B2J. We're still in the jth column. Up to the nth row, right? B is a P by Q, so there are P rows. But as n equals P, we can stop with B and J. All right. Well, we know how to carry out a multiplication between a row and a column matrix. We multiply corresponding entries and add them up. So this will be Aij times AI1 times B1J plus AI2 times B2J plus up to the last pair of entries, AIN times B and J. Now you have it. You have the sum, and we can write this much more concisely using sigma notation. So what are we summing? We are summing entries of A times entries of B. So A, B. Now the row index of A is always I, AI1, AI2, up to AIN, so that does not change. So AI. The entries of B are always from the jth column, B1J, B2J, up to BNJ, so that does not change. What changes is the column index of A and the row index of B, right? So this is 1, 1, 2, 2, up to NN. We need a dummy variable to capture this change. We will use K. So AIK, BKJ. Where does K start? K starts at 1. So K is 1. You get AI1 times B1J. Then K will be 2, AI2 times B2J. Then K will be 3, AI3 times B3J, up to the very last term when K equals N. So AIN, BNJ. So K begins at 1 and it ends at N. Let me just tweak this a little bit further. I will simply rewrite lowercase a with an uppercase A but using round brackets. So the sum from K ranging from 1 to N, the entries of A in the ith row, kth column, times the entries of matrix B in the kth row, jth column. And one thing I'll do is I'll actually drop the beginning and the end of our summation. I'll simply write the sum over K, meaning we sum over all possible values of K. K obviously beginning with the first entry, and it ends with the last entry. So we sum over all possible values of K, the entries of A in the ith row, kth column, the entries of B in the kth row, jth column. And this is what you use when you want to prove properties of matrix multiplication. Remember, this was simply the entry in AB found in the ith row, jth column. So we always use this for calculations. You take the ith row of A times the jth column of B. But for a proof, we will use this result. And this is the entry in AB found in the ith row, jth column. And let me show you how you can remember this really, really naturally. If you remember that when you multiply matrices, you will simply multiply a row times a column. And when you do so, you multiply corresponding entries and you add them up. So we're done with our definition, but let me just give you a trick to remember this formula. This one should be easy. If you want the entry in AB in the ith row, jth column, take the ith row of A times the jth column of B. And let's see how we should write this naturally. So if I ask you for the entry in the new matrix A times B, found in the ith row, jth column, well, we take the ith row of A times the jth column of B, right? So you say, okay, well, if we take the ith row of A, we take the entries of A found in the ith row. So this would be the entries of A. Since we take the ith row, the first index is fixed, it's I. Then we take the jth column of B, well, entries of B, found in the jth column, that is the second index, that is also fixed. And if you think of it, we multiply the ith row of A times the jth column of B, but how do we multiply a row times a column? We multiply corresponding entries. So 1 with 1, 2 with 2, 3 with 3, 4 with 4, 5 with 5, and so on. In general, the kth entry in row I of A with the kth entry in column J of B. So we multiply corresponding entries, K being our dummy variable, and we add them up. And this is how you should remember this expression. We take the ith row of A, jth column of B, multiply corresponding entries, and we add them up. Before we look at actual proofs, let's consider a few examples to see that this may look a bit complicated, but it's actually not so bad. Let's do a few examples of matrix multiplication. The properties of matrix algebra with their proofs will be in future videos. We'll now simply look at examples to show you that it may look complicated, but it's not that bad, so we get the hang of it. So example number 1, let's take A to be, say, a 2 by 3 matrix. So 1, 2, 3, negative 2, 1, 4. And we'll take the matrix B to be, say, a 3 by 2. So 1, 1, 2, 5, negative 3, 1. So the first question is, can we multiply A by B? Can we do, or I should say A times B? Let's see. A times B. Well, A is a 2 by 3 matrix, 2 rows by 3 columns. B is a 3 by 2 matrix, 3 rows, 2 columns. So the first question is, can we multiply A with B? Well, the answer is yes, right? 3 equals 3. So we're good. And the new matrix will actually be a 2 by 2 matrix. Let's see how that's going to work out. So let's write our matrix A. 1, 2, 3, negative 2, 1, 4, times the matrix B, 1, 1, 2, 5, negative 3, 1. So we know the new matrix AB will be a 2 by 2 matrix. Let's compute one entry at a time, right? This is the new matrix A times B. We'll go slower for the first few examples, but very soon you'll see how you can pick this up. You'll be able to go from here to here directly without any steps on the side. But as this is our first example, let's go slowly. Let's find the first entry here. So this is the entry in row 1, column 1. So you say, okay, well, we want the entry of AB in the first row, first column. Well, we take the first row of A, so it's the row 1, 2, 3, times the first column of B, 1, 2, negative 3. And we know how to multiply a row times a column. We multiply corresponding entries and add them up. So 1 times 1 plus 2 times 2 plus 3 times negative 3. So what do we have? We have 1 plus 2 times 2, 4, plus 3 times negative 3, negative 9. So in the end, we're left with 1 plus 4, 5 minus 9, negative 4. And so you see the entry of AB in the first row, first column is simply negative 4. Let's compute now the entry in row 1, column 2 of AB. Well, once again, we take the first row of A, 1, 2, 3, times now the second column of B, 1, 5, 1. And this is again easy, multiplying corresponding entries and adding them up. So 1 times 1 plus 2 times 5 plus 3 times 1 we are left with 1 plus 10 plus 3, 11 plus 3, 14. And so we have our other entry in row 1. The entry in row 1, column 2 is 14. And if you notice, and this is what we will take advantage of very shortly, when you multiply a matrix A times B, always build the new matrix one row at a time. You see, how did we construct the first row of AB? Well, if you look here, we took the first row of A, the first row of A, and we went through the columns of B. You see, we took the first row of A times the first column of B, and we have the first entry in our first row. If we keep going, take the first row of A times the second column of B, you will have the entry in your new matrix in the first row, second column. And now we will repeat. If you want to build the second row of AB, simply take the second row of A and go through every column of B. This row times this column will give you this entry. This row times this column will give you this entry. Let's do it on the side for now, and then in the next example, we'll go a little faster, going one row at a time. We'll fix the row of the first matrix and go through the columns one at a time. That way we will construct AB one row at a time. Okay, well, this is the entry in AB now in the second row, first column. So this is AB 2, 1. So we take the second row of A, negative 2, 1, 4, times the first column of B, 1, 2, negative 3. Let's multiply corresponding entries and add them up. So negative 2 times 1 plus 1 times 2 plus 4 times negative 3. Well, we get negative 2 plus 2 minus 12. So in the end, we're left with negative 12. So this is the entry in row 2, column 1. So it's the entry here. And finally, let's compute AB 2, 2, second row, second column. Well, the second row of A, we already have it. Negative 2, 1, 4. Times now the second column of B. Well, if you look up, this is matrix B. Its second column is 1, 5, 1. So we get negative 2 times 1 plus 1 times 5 plus 4 times 1. So we get negative 2 plus 5 plus 4. 9 minus 2, positive 7. And so we have the entry in AB, row 2, column 2 is 7. And there you have it. We have computed our first non-trivial matrix multiplication. The matrix A times the matrix B is a 2 by 2 matrix, and it is given by negative 4, 14, negative 12, 7. Let's now ask, can we compute B times A? All right, we just computed A times B. Let's see if we can compute B times A. And let's see if something interesting happens. And now we will compute B times A directly without doing all of this work on the side, keeping in mind to construct the new matrix AB or BA as in our case, we fix a row of the first matrix and go through the columns of the second, which will construct the first row of our new matrix. And then we will fix row 2, go through the columns, and build the second row of our new matrix, and so forth. So let's now look at B times A. Can we compute it? Well, B is a 3 by 2 matrix, and A is a 2 by 3 matrix. So 2 equals 2. So indeed, we can compute B times A, and the new matrix will be a 3 by 3 matrix. And this is kind of interesting because you see, A times B was defined, but it was a 2 by 2 matrix. Now, if we flip the order and do B times A, it's also defined, but it will no longer be a 2 by 2 square matrix, but it will be a 3 by 3 square matrix. So you see that A times B is not equal to B times A. Let me just write the two matrices. B was the matrix, if you remember, 1, 2, negative 3, 1, 5, 1, times the matrix A, which was 1, 2, 3, and then negative 2, 1, positive 4. And the new matrix, as we have just said, will be a 3 by 3 matrix. And we will construct the matrix AB, as we have just said before, one row at a time. Okay, so let's construct the first row by fixing the first row of B and going through each column of A one at a time. So we fix the first row and we go through the first column. So you have 1 times 1, 1, plus 1 times negative 2, negative 2. So 1 minus 2 is negative 1. So we have the first entry of our first row. Let's keep going. We again fix the first row times the second column. 1 times 2, 2, plus 1 times 1, 1. 2 plus 1 is 3. Second entry of our first row. And finally, times the third column. So 1 times 3, 3, plus 1 times 4, 4. 3 plus 4 is 7. And so you see very easily by fixing the first row of B and going through each column of A, we now have the first row of, matrix B times A. Well, to construct its second row, we will now fix the second row of B. So 2 times 2, 2 times 1, 2, plus 5 times negative 2, negative 10, 2 minus 10, negative 8. Let's keep going. 2 times 2, 4, plus 5 times 1, 1, 4 plus 5, 9. And finally, 2 times 3, 6, plus 5 times 4, 20. 6 plus 20, 26. And we now have the second row of BA. To construct its third row, we will simply fix the third row of B and go through every column. Negative 3 times 1, negative 3, plus 1 times negative 2, negative 2, negative 3 minus 2, negative 5. Negative 3 times 2, negative 6, plus 1 times 1, 1, negative 6 plus 1, negative 5. And finally, negative 3 times negative 3, negative 9, plus 1 times 4, 4, negative 9 plus 4, negative 5. And now we have the matrix BA. So you see, once you're comfortable, you don't have to write out all of this. You can simply do it in your head. But always be systematic when you construct a product of two matrices. Always construct it one row at a time by fixing a given row of the first matrix and going through every column of the second matrix. And you can appreciate how different the answers are in the case of AB, it being a 2 by 2, and in the case of BA being a 3 by 3. Let's do another example that is even more radical, but we can see at least, even though both AB and BA are defined, they're not equal. And this is true in general. In general, matrices do not commute under multiplication. So you have to be very careful. When you handle real numbers, you're used to saying a times b equals b times a, because real numbers do commute under multiplication. It is unfortunately not the case of matrices, as was proved in this example. Both a and b were defined. AB was a 2 by 2 matrix, but BA is a 3 by 3 matrix. Let's consider one more example that is even more radical, where AB will be defined and BA will not be defined. This is our third example. Let's take, say, a 3 by 3 matrix for A. So 1, 3, negative 2, 1, negative 1, 1, 4, 5, 1. Let's take B to be, say, a 3 by 2. 1, 3, 9, negative 1, negative 1, 2. Let's look at A times B. Can we compute A times B? Well, A, as we've said, is a 3 by 3 matrix. B is a 3 by 2 matrix. 3 equals 3, so we can multiply A times B, and the new matrix will be a 3 by 2 matrix. Let's perform our multiplication. So 1, 3, negative 2, 1, negative 1, 1, 4, 5, positive 1, times the matrix B, 1, 3, 9, negative 1, negative 1, 2. The result, as we have just said, will be a 3 by 2 matrix. So 3 rows and only, 2 columns. Let's construct the first row by fixing the first row of A and going through the 2 columns. So 1 times 1, 1, plus 3 times 9, 27, 27 plus 1, 28, plus negative 2 times negative 1 plus 2, 28 plus 2 is 30. Let's now go over the second column. 1 times 3, 3, plus negative 3 is 0, plus negative 4, and so we get negative 4. Let's now construct the second row by fixing the second row of A. So we get 1 minus 9, negative 8, minus 1, negative 9. Let's go over the second column. So 3 plus 1, 4, plus 2, 6. And let's now construct the third row of AB by fixing the third row of A. So we get 4 plus 45, 49, minus 148. Then we get 12 minus 5, 7, plus 2, 9. And now we have matrix AB. Let's now ask, can we multiply B times A? Well, B is a 3 by 2, A is a 3 by 3, but the number of columns of B does not equal the number of rows of A. And so the multiplication is not defined. B times A does not exist. So you see in the previous example, both AB and BA were defined. They both existed. AB was a 2 by 2 matrix, BA was a 3 by 3 matrix. They were not equal, but they both existed. This example is even more radical because AB exists, but BA is not even defined. And if you think of it, it's pretty clear, right? Suppose you tried. Even if you don't look at this, you'd say, well, let's see if I can do B times matrix A. Well, you would have to find the entries of this new matrix by doing some row of B times some column of A. But if you think of it, you only have two entries in any given row of B, and you have three entries in any given column of A. And so you cannot multiply a row times a column unless they have the same number of entries. And you see why BA indeed does not exist. So just to show you that, again, in general, AB does not equal BA. So you have to be very careful about this. When you manipulate matrices algebraically, you have to remember that they do not commute under multiplication. One last little example, and this is something that is very natural. You could ask, well, can we take, let's say, powers of a matrix? Can we multiply a matrix with itself? Well, let's see. What if we take A to be a rectangular M by N matrix, and we ask, can we perform A times A? Well, A is an M by N, A is an M by N, and you can only multiply A with itself if N equals M. But if N equals M, that means that the number of rows of A equals the number of columns of A, and so A would be a square matrix. And so you see, you can only multiply a matrix with itself if it is a square matrix. So if M equals N and vice versa, so of course the matrix A times A will simply be an N by N because M equals N. So we can only multiply a matrix with itself if the matrix is a square matrix. And of course, now if you say if you have a square matrix, then how can we write this concisely? You can say, well, I can do A times A. I could also do A times A times A. I could also do A times A times A times A and so forth. Well, we'll use the same notation as we use for real numbers. This is simply denoted by A squared, A cubed, A to the 4, and in general, if you write A to the K, where K is some positive integer, K is a positive integer, right? Z plus denotes the positive integers. If you prefer, that's equal to the set 1, 2, 3, and so on, only positive integers. Then A to the K is simply A times A times A, exactly K times. You may wonder, well, what about, say, negative powers, negative exponents? And we will see this later on. For now, only think of positive powers, 1, 2, 3, up to infinity, where A has to be a square matrix. If A is not a square matrix, you cannot take powers of it. And this will be your last example. Let's take a simple 2 by 2 matrix, and let's find, say, its third and fourth power. So let A be a 2 by 2 matrix. So let's go with 2 negative 3, 1, 4. Let's compute a squared, a cubed, and a to the 4. So if we do a squared, this is a times a. So 2, negative 3, 1, 4 times itself. 2, negative 3, 1, 4. And as we just saw, if you multiply a square matrix with itself, the size does not change, right? This is a 2 by 2 matrix. This is a 2 by 2. 2 equals 2. So we can multiply, and the result is a 2 by 2 matrix also. As always, we fix a row of our first matrix and go through the columns. So 2 times 2, 4, minus 3, 1. 2 times negative 3, negative 6, minus 12, minus 18. Then we have, with the second row of A, 2 plus 4 is 6. Negative 3 plus 16, positive 13. And now we have just found A squared. Let's compute A cubed. Of course, now we won't go back and do A times A times A. Because if you think of it, A cubed is just A times A squared. And we have just found A squared. You say, well, okay, A is 2, negative 3, 1, 4, times A squared, which is 1, negative 18, 6, positive 13. The result will still be a 2 by 2 matrix. Let's see. We'll have 2. Again, we construct our first row. So 2 minus 18 minus 16. Then we'll have 2 times negative 18, negative 36, minus 3 times 13, negative 39. Which gives us negative 75. Then, with the second row, 1 plus 24, 25. Negative 18 plus 4 times 13 is 52. Gives us positive 34. And so we have now A cubed. And we can compute A to the 4. Now if you think of it, well, we could do A times A cubed. But one thing is worth mentioning is we could have found A 4 without finding A cubed. If you think of it, suppose we had asked to find the fourth power of A. What's the shortest way? Do we find A squared, then A cubed, then A to the 4? Or can we actually skip from A4, from A2 to A4? And the answer is yes, because A4 is simply A squared times A squared. So we'll get 1, negative 18, 613, times 1, negative 18, 613. Of course, at this point, you could have also done A times A cubed and obtained the same result. So we'll have 1 minus 6 times 18, negative 107. Then we'll have negative 18, negative 18 times 13, negative 252. Second row, 6 plus 13 times 6, 84. And finally, last entry, 6 times negative 18 plus 13 times 13, positive 61. And now we have A to the 4 by doing A squared times A squared. Just for good measure, let's do A times A cubed and see that we get the same answer. matrix A, 2, negative 3, 1, 4, times A cubed, negative 16, negative 75, 25, 34. So 2 times negative 16 plus 3 times negative 25, negative 107 as before. Second entry, 2 times negative 75 minus 3 times 34. Negative 252 as before. Second row, negative 16 plus 100, 84. And negative 75 plus 4 times 34 gives us 61. So everything worked out. But keep in mind that, and this is worth mentioning, you can find a to the 4 without finding a cubed by simply doing a squared times itself. And this is the method that's called repeated squaring. You could then find, if you wanted, a to the 8 by doing a to the 4 times a to the 4, and so on. This completes our discussion, or at least our introduction, of matrix multiplication. In our next video, we will consider properties of this operation with matrix addition and matrix multiplication and prove those properties using sigma notation. Oh, and actually I forgot, let me give you one last definition. And the question is, if you remember, the analog of the zero real number was the zero matrix. If you add to a matrix the zero matrix, the matrix where every entry is equal to 0, you get the matrix back. And the question would be here with multiplication, what is the analog of the real number 1 in the case of matrices? And if you think back, what is the defining property of the real number 1? If you do 1 times any real number A, or A times the real number 1, you get A back. The question is there a matrix that behaves the same way? And the answer is yes, and we will denote this matrix by I. So there is a matrix such that I times the matrix A, if A is square, is the same as the matrix A times I, which actually is just A. The question is, well, what is this matrix? Well, I'll simply give it to you, show you a simple example, and I will leave the proof to later. This matrix will be called the identity matrix. And you have one for each size. So you have a 1 by 1, a 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on, identity matrix. It will simply inherit the size of A. If A is, say, 5 by 5, I will be 5 by 5. If A was 10 by 10, I would be 10 by 10. So you may ask, well, what if we have a 1 by 1 matrix? I would simply be the 1 by 1 matrix 1. If A was 2 by 2, I would be the matrix 1, 0, 0, 1. If A would be 3 by 3, I would be a 3 by 3 matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. If A were 4 by 4, I would be a 4 by 4 matrix. And you can see the pattern, right? If you think of it, the simplest way of describing this matrix is, on the main diagonal, the entries are 1. Off the main diagonal, the entries are 0. So this would be 1, 1, 1, 1. Zeros everywhere else. So 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so forth. So in general, we can define I, if it's an n by n, quite simply, right? So we will write simply the entries of the matrix I in the ith row, jth column, what are they? Well, they are equal to 1 if we are on the main diagonal. You say, well, how do we say this? Well, if you think of it, this is the entry 1, 1, 2, 2, 3, 3, 4, 4. So you are on the main diagonal if the row index equals the column index, so if I equals j. And of course, if I is not equal to j, then you are off the main diagonal. This is a simple slash. So if I is not j, then you're off the main diagonal, and the entries are simply equal to 0. And this is how you define the identity matrix. 1s along the main diagonal, 0s everywhere off the main diagonal. Let me show you a simple example of a 2 by 2 matrix, and then later on we'll prove that this works for any square matrix A. So take the matrix 2 by 2 I matrix, so 1, 0, 0, 1 times the matrix 3, 4, negative 5, 6. Well, we'll have 1 times 3, 3, plus 0, so it's just 3. 1 times 4, 4, plus 0, 4. 0 minus 5, minus 5. 0 plus 6, plus 6. And you get back, of course, the exact same matrix. And it works both ways. If you did the matrix A first, times I, you get 3 plus 0, 3. 0 plus 4, 4. Negative 5 plus 0, negative 5. 0 plus 6, 6. And once again, you get back the matrix A. And this works for any square matrix if you take I to be, again, the matrix of the same size, where you get 1s on the main diagonal, 0s off of the main diagonal. And that's it.